turbo engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
discoveries,
Advances.
questions,
Research.
technology.
Unbelievable.
Without further ado,
This is The Naked Scientists. Hello, Happy New Year. It's Q&A time. You supply the questions, we supply the answers. Coming up, how stars burn for billions of years, can Rishi Sunak succeed in turning us all into a nation of mathematicians, and the way that information, or even misinformation, can change the shape of our brains. This is The Naked Scientists.
The Naked Scientists podcast is powered by ukfast.co.uk.
And with me to help answer those questions that you're sending in are Tom Mustill. Now, he's an award-winning natural world filmmaker. He's directed some David Attenborough, including Giraffes, Africa's Gentle Giants. He's also an author. And I gather recently you've been diving into the underwater realm. Tell us more.
Well, yeah, I've got a sort of quite weird link to whales in that in 2015 I was kayaking and a humpback whale breached on top of me and dragged me and my friend underwater, and we were fine and the whale was fine. But I was already quite interested in whales, but that definitely made me more interested in whales.
My goodness, because there was some very famous footage that made the internet of some people getting body slammed effectively by a multi-ton, because they weigh a lot. I mean, they're tens of tons, aren't they? Or was this a big one?
This was a big one. It was a humpback. It was an adult. The rule of thumb with humpbacks is you get about a ton a foot, and it was about 30 foot, so about 30 tons.
And do you know why it decided to come down on top of your kayak?
Well, this was the thing that I found most interesting as a zoologist by background and then a wildlife filmmaker, was when a whale jumps out of the water, you know, it releases the equivalent of like 30 hand grenades worth of power, and no one knows why they breach. No one has. There was a lot of theories, but really they're just conjecture at the moment. We don't know why they breach at all. And the only thing we really know about that incident when it landed on us was that it probably wasn't on purpose, because scientists analysed the trajectory of the whale and they found that in midair it looked at us and it turned away and intentionally moved away from squishing us, and that's why we survived.
Well, that's interesting that it would have had a concept that this would be potentially lethal for you had it splatted.
Well, it's unclear.
Or was it thinking it was self-preservation? I don't want to hit that hard-looking thing.
I think like the scientist in me thinks, well, the most rational thing is, it sees a new object and wants to not hit it. But humpback whales in the last few years, there's over 100 incidents where they've come to the aid of other species when they're in trouble. So and I witnessed this. I witnessed humpbacks pushing killer whales off a dead grey whale calf that the killer whales had hunted. And all over the world, in all the oceans, humpback whales interfere to try and preserve the lives of other species. So maybe there was some altruism in there too.
Well, Tom Mustill's with us. He's the author of How to Speak Whale. He's brought a copy of his book in. He'll be answering questions and telling us about how whales communicate later on in the programme. Next up, Lior Zmigrod is a psychologist. She's at the University of Cambridge. She's got a broad expertise in psychology, but she's very interested in extremism. Specifically, what are you interested in? Is this the area of sort of susceptibility to extreme beliefs? Why are extremists sort of born not made, or do they get converted by hearing the wrong thing? Is that the area you're interested in?
That's right. In psychology, we use a lot of methods from kind of social sciences to try to understand what factors make people susceptible to radicalizations or to taking ideologies to an extreme degree. But I'm actually interested in the brain and what characteristics of your brain, of my brain, might make us susceptible or resilient in the face of extreme ideologies. So
that's Lior Zmigrod. Matt Bothwell's also in. He's the University of Cambridge's public astronomer, and he's also an author. The Invisible Universe, Why There Is More to Reality Than Meets the Eye is Matt's book. Now, you were on this programme at almost the same time last year, Matt, and the conversation we were having then was the debate in your house about turkey and tinsel versus telescope, because it was just after Christmas and the James Webb Space Telescope had launched, and you said you eschewed the Queen, you eschewed the Christmas table, and you watched the telescope go up. So what's on your radar for 2023?
Well, more James Webb to start with. The last year has been a fantastic one for James Webb. Listeners might have heard that one thing that we were really concerned about as astronomers was the amount of fuel left for operations, because it was the same fuel tank was doing the launch and then would have to be up there steering the telescope. And it turns out that the launch was so precise, we might have as much as 2 decades of James Webb. And the first year has surpassed all expectations, and we have lots and lots of exciting things coming in 2023. I think for me personally, I'm most excited about a satellite called Euclid, which is going to be launching sometime in the summer. It was going to be launching earlier, except it was going to go up on a Russian rocket, and sort of geopolitics has intervened. But sometime between June and September, I think Euclid's going up, and what it's going to do is measure the acceleration of the universe more accurately than ever before, and that's going to give us all kinds of important information about how dark matter works and how dark energy works, and hopefully give us the keys to some very, very big questions indeed.
This is the issue that the universe, if we look far enough away, we see things retreating from us, and the farther away we look, the faster they're going away. Evidence the universe is getting bigger all the time.
Exactly, yes. Well, it's a little bit more than that. So we've known that the universe is getting bigger and bigger all the time for about a century now. But around the year 2000 or so, scientists tried to measure exactly how fast the universe was getting bigger, because we expected it to be slowing down, right? Like something slowly grinding to a halt. But it turns out it's the opposite. Something has its foot on the accelerator of the universe. The universe is getting pushed apart faster and faster and faster by some mysterious force that we don't understand. We call it dark energy. Astronomers use the word dark to mean I have no idea what this thing is, right? So, yes, we're trying to understand more about this mysterious force that seems to be pushing the universe apart.
Thank you very much, Matt Bothwell. Also with us, Ems Lord, who is the director of Enrich. She is Cambridge University's Maths Outreach Programme Director. That's really relevant to you, I would think, what Rishi Sunak has said this week. He wants to turn us all into a nation of mathematicians. He wants everyone studying maths till the age of 18. What do you think about that?
Oh, wow. I mean, what a great week to be a mathematician. We're suddenly front page news. It's great that there is this conversation going on about mathematics and the study of it. But then you take a step back and just say, how will we deliver this? Where's the maths teachers for a start? We already have a shortage. Where are we going to find them from to quickly deliver this? But also, when you look at some of the research reports about why people don't carry on with maths, there's one in particular that really grabs the attention, and the title, I Would Rather Die. This is a study, seriously, this is a study among teenagers, 16-year-olds, about why they don't want to carry on studying maths. And they would rather die.
They'd rather go boating with Tom than...
So, yeah, they don't mention the whales. But, this is the issue we have. It's the curriculum, the maths curriculum. We're teaching things that we maybe taught 50 years ago that were relevant. And now we've learnt through COVID how important it is to have data literacy. And
is he confusing numeracy with maths? Is that because when I saw the example you just gave, and I saw umpteen newspapers in the last day since the Prime Minister said, I want people studying more maths, they're all giving examples of what I would call numeracy, the ability to understand when you're being ripped off, to understand how to get a good deal, how to work out how much carpet you want in your living room. But that isn't maths. That's an application of maths. That's being numerate. Maths, to me, is when you try and explore the relationships between numbers and interesting concepts. That's slightly different. So are they kind of selling this as maths and it's not?
Yeah, they're talking about numeracy and some very basic examples. What they're not talking about is understanding statistics. So if you hear a survey, 90% of people think this is a great idea. How many was the 90%?
Yeah, how many people? Because if they interviewed 10 people and it was 9 out of 10, okay, meaningful. If you interviewed 2 people...
And nowadays, isn't that such an important skill to have when we're being bombarded with these images and these surveys? These things weren't happening 20, 30 years ago. We had a few years ago Michael Gove going into schools when he was the minister. And this guy was so taken with long division and how he learnt at school. We suddenly have primary schools now teaching long division again. And yet we have calculators. Let's think about the numbers we're producing and have the number sense to interpret the data and use it to make good decisions. So if we're talking about having maths and becoming data literate, that's fantastic, but we need the funding and we need the teachers to make it happen.
I think we're going to have a good programme and a bit of fun this week. So that's our panel. Thank you, Ems, by the way. Let's circle back and begin with you, Lior. This is a question that James has sent in, and I can identify with this. I have a black Labrador. In his case, he says he's got a golden retriever, and in his words, it has a tremendous urge to carry things around. I can't even take a walk without the dog turning up with a stick or something. We've never taught him to retrieve these things. He just started doing it. I believe he was born with it. So can you please explain, he says, whether or not it's understood how behaviours and even certain skills, which appear to be genetically passed on, get encoded into the brain like this? What do you think?
Wow, what a big question. And I guess when we're thinking about how things are passed on genetically in terms of evolution and how that gets into our psychology, there are some overlaps between animals and humans, but there are also some differences. So, with golden retrievers specifically, we know that they've been bred to retrieve. So the fact that then they can do that very well is not surprising because their evolution has kind of been fast forwarded to be able to do that really well. For humans, I guess the question is, why don't we all retrieve constantly? There, it's a question of personality. We see even babies as young as a few days have personalities and temperaments. Some are irritable and some are calm. And that's obviously not something that they learnt. It was just something that they were born with.
But to the root of the question, which is, does anyone know actually what's going on in the brain in a retriever that wants to retrieve versus a dog that just wants to run off and play? Have we got any insights yet into how genetics translates into brain structure that encodes these sorts of hardwired behaviours? A bird building a nest, for example.
So there's a whole line of research called comparative psychology or comparative cognition that looks at the skills that animals have and why they have those skills. And so, for instance, we know that different kinds of birds and corvids are exceptionally good at problem solving. So why that actually happens, I think that it's a really long chain of kind of causes and effects. And I don't know if, as a science, we have it all down to one long trajectory that we understand. We know that our genes code for particular kinds of proteins, and that those proteins are then used in our biological functioning, and that gets translated into our whole way of living and how animals behave as well. But the whole chain, I think that's a really big question.
Anything from the whale perspective, Tom?
Well, I'm not sure people know very much more about how whales convert their genetic programming or their neurochemistry or neurobiology into communication. But we do know that they pass on complex behaviours from one to another while they're alive. And researchers who study whales go as far as to call these cultures. So, for instance, in sperm whale populations, in some places you have whales that look exactly the same to me or you. But when they come into contact with each other, different populations won't interact at all. And they'll act in totally different ways. They'll forage in different ways. They'll defend themselves in different ways. They'll even communicate with different accents and what it seems like different communication systems. And they learn these from one another. So if you were to take one of these whale babies away at birth and keep it by itself, it wouldn't do any of those things. Those things aren't instinctive. They're not programmed into them. And we really haven't been looking for a very long time at culture in non-human animals. And in the research that I've done, we seem to find it in more and more places. We find learnt behaviours passed down from one animal to another. And combined with the emerging studies of animal personalities, one fox is not like another fox, you're getting a picture of much greater complexity in how animals do things and why they do things and how that differs between them than we thought there was before, and that can simply be explained by differences in genes or brains.
All fascinating stuff. Ems, one for you. I gather you're going to be speaking at the Cambridge Festival later on in the year. You're going to talk about number sense specifically and how having a bit more of that could help everybody, really. So what's really the thrust of your argument for that?
Well, number sense is something that gets overlooked so easily. We focus, I mentioned before, long division, long multiplication, doing procedures. But when was the last time you're in the supermarket queue and you're trying to work out, did you have enough to cover the bill? And you went, oh, it's okay, I've got some squared paper and a pencil and a ruler. I'll just quickly do a bit of long division or multiplication and I'll figure the whole thing out. Life doesn't work that way. You find yourself in a situation, you're at the petrol station, you're paying, you've got to quickly deal with numbers, and you've got to have a feel for numbers and know if you've got it right or wrong. And that's what we call number sense. So it's not just knowing the facts, it's having the confidence to play with it and recognise mistakes. So what I like to do is find out when it's gone wrong. Okay, I like the disasters, I like the mistakes, and then see what we can learn from them. So what I've come up with is a top 5 of IT disasters. These are projects where people have been incredibly ambitious and said, we want to go to Mars, we want to have the biggest subs, we want to have the fastest trains. So they're ambitious projects. These are projects that have secured funding. So they have gone through loads of different levels. As we all know, when we try and get funding, not easy. So you've got an ambitious project, you've got it funded, and then it fails at the end in a very embarrassing way because of number sense. And quite often, one of the things that happens is the conversion from metric and imperial.
There's a spacecraft that had a problem, very expensive consequence. Well, you're nodding, Matt. It's quite a classic one, that, isn't it? The difference between imperial and metric.
Yes, exactly. I think there was I forget the exact details. I think it was a European spacecraft that was using a software program designed by Americans. And the software program supplied an acceleration in sort of foot-pound hectares or whatever stupid thing Americans use. And then the spacecraft interpreted that as a metric and crashed into Mars.
Costly mistake. So you've got
8 million costly mistake. 2 years development, 9-month journey. They got it there. They got it into the Martian atmosphere. And that's when they lost it. I mean, how much do you feel? You're sat there following this for months. You've got an investment, a long-term project, and it burns up at that point. I just can't imagine how those guys must have felt.
I know.
Very nasty. Would being better at maths have spotted that, though? If I had a bit more numeracy, would I necessarily? I mean, these are bright people, and if they don't spot that, why do you think a paucity of maths ability is the problem?
I think it's what we value. At the moment, what we tend to value is, did you get the right answer? Okay, have you got an answer? Move on to the next one. Our exam system favours that. Even down in primary school, you get a 20-question booklet. How quickly can you get it through? They aren't encouraged to check and look back and estimate. And the mistakes that I'm looking at, you could avoid through that. You could save your 328 million just by going, do you know what? Those figures don't look right. But too often we trust everybody's figures and we don't sit down and go, do you know what? That sort of sucking of teeth you might get when someone's doing DIY. Measure twice and, check it carefully.
I've learned that the hard way. I do a lot of mechanical type stuff. And I had to find out the hard way. You measure twice, cut once. And
exactly.
You're nodding as well, Tom. So.
Well, I just love this idea of number sense and the idea of questioning things, because I think so many people get turned off many sciences when they're at school because there's an idea that you have to memorize what's right or wrong. And it's only really when you get into doing your own research and you know a topic really well that you realize that most people aren't really sure of all the things that you learnt at school, and that the most exciting things are mysterious, and probably most of the things that are thought to be right will be wrong at some stage in the future. And that's so much more exciting than proving whether your brain can remember stuff. This idea that, for example, in natural history, we have so few explanations for so many of the things that animals do. And I think that's really exciting. And I think many more people will be drawn into it with this idea that they can contribute and play rather than don't get it wrong.
Yeah, it's the excitement of what we don't know rather than getting right just what we think we know. As ever, if you have a question for a programme like this, you can get in touch via email. It's chris@thenakedscientist.com, or you can tweet @nakedscientists. Off the planet now. This one, definitely for you, Matt. Dwayne has said, since stars are emitting so much energy constantly, how can they last for millions or billions of years? I would expect them to burn up much sooner.
It's a really good question. I think I'm going to give you an answer in two halves, I think. You wouldn't be alone in thinking they would burn up sooner. Around 100 years ago, this was one of the real hot topics in physics. There was a famous physicist called Lord Kelvin around the start of the 20th century, did a sort of back-of-the-envelope calculation of how long the sun should last and came up with an answer of a handful of million years. He sort of imagined the sun is burning like a gas fire or something and said, okay, it can last maybe 10 million years. And therefore, evolution has to be wrong. There's not enough time for animals to evolve. And he used that to argue against Darwin. And of course, he was completely wrong, right? The missing piece of the puzzle that he didn't understand was the process that the sun uses to create energy is called nuclear fusion. And it's extraordinarily efficient. You get an enormous amount of energy out of a really, really tiny amount of matter. It's dictated by this very famous equation, E equals mc squared. E is energy, m is mass, and c is the speed of light, which is a very big number. So c squared is an enormous number. So what E equals mc squared is really telling you is that a tiny, tiny bit of mass gives you an enormous amount of energy. Stars are very, very efficient. The other half of the answer is that stars are just really, really big. So even if they are churning through fuel at an enormous rate, they can still last a very long time. The sun burns through several million tons per second, which sounds unbelievable, right? You think that wouldn't be sustainable at all, but if you go and calculate it out, maybe use your number sense, right? If you get a calculator, work out how many seconds in a year, multiply that by 10 billion years, and multiply that by 1 million tons a second, you don't get to even a fraction of 1% of the sun's mass, right? So the sun can happily burn 1 million tons a second for billions of years and still be absolutely fine. And it's all down to the efficiency of E equals mc squared.
One point, though, is that size matters when it comes to stars, doesn't it? Because if you are a very big star and you have a massive amount of fuel and a massive amount of gravity and mass driving it all together, you get very, very hot very, very quickly, but you also burn off all that fuel much more quickly. So big stars burn faster and brighter than small stars.
Yeah, that's exactly true. It's almost counterintuitive, right? You would think big star, more fuel, it would last longer, but big stars really do sort of live fast and die young. They burn so hot, they burn through their fuel much, much more quickly than smaller stars. So a star like the sun, which is pretty small, would last about 10 billion years. That's about 10,000 million years, more or less. A massive star might last 10 million years, which sounds like a long time. It's sort of a blink of an eye compared to the sun. A little cold red dwarf star might last for longer than the age of the universe.
Thank you, Matt. Let's come back to you, Lior, back down to Earth, both physically as well as metaphorically. Now, we've often talked on this programme about fake news and its impact in various ways. You're very interested in who's susceptible to these sorts of messages. So is there a kind of classic type of victim? We were talking just now and you were helping us understand about golden retrievers having innate abilities to go and retrieve sticks and slippers and so on. So are there people who are born susceptible to these sorts of messages?
So what we've seen in the research that I've done and the research that a lot of people have done as part of this new field called political neuroscience, which is using neuroscience techniques to study our political ideologies, what we find is that there are some traits that we can measure in the brain, in our cognition, we might not even know that we have, that we might not be able to self-report on what we are. And we can use those traits to infer who is most susceptible to things like radicalization. One example that I found in my research is a trait called cognitive rigidity. So we measure cognitive rigidity by basically getting you to play all these kinds of brain games where you're moving shapes on a screen or you're responding to all sorts of challenges. Some might be numerical challenges, some might be linguistic and kind of language games. And what we see is that people who kind of cling on to first impressions and then never manage to change or to switch or to adapt. People who are cognitively rigid, who mentally tend to stick to their first guns and then never change, even in tasks as simple as kind of like Tetris-like games. The more rigid they are, cognitively, psychologically, the more that they're also rigid in their politics and in their ideologies. So that's one kind of factor that makes people susceptible to becoming radicalized to any ideology.
So that could work both ways then, because if they're not radical, they're not going to be very susceptible to being radicalized. But if they are a bit radical to start with, then it's very hard to shake them out of it.
That's a great point, that there's a kind of this paradox of flexibility and rigidity, right? If you are too rigid, you'll never let any new ideas in. But if you're too flexible, you'll kind of sway with the wind. Whatever the latest opinion is, that's the fashion that you'll take on to. So there is kind of this middle ground in order not to be either too persuadable or too dogmatic.
There's been some criticism recently of the programme that the UK government set up called Prevent, which was the idea being that you try to stop people becoming seduced by terrorist messages and extremist ideologies, for example. And people were saying that this was flawed. If we've got people in the population, though, who are very rigid in their thinking, we know they all exist, but if they're already terrorists, does this mean, or they have inclinations to become terrorists, does this mean that we really can't, with all the best will in the world, make a programme work that will change their mind?
I don't think so, because there is a difference between vulnerability, which is like a potential state, and actuality, what you actually end up doing. So even if we have a population and kind of a large range of people who might be susceptible to ideological extremism or to becoming radicalized, that doesn't necessarily mean that they will. And so finding out who is vulnerable and how we can best support them before they end up being exposed to radical ideology, I think that that's important.
Leo, thanks very much. More questions coming up in just a second, but we're now bound for our quiz. So get your pens and pencils ready. We'll be testing your metal general knowledge and the general knowledge of our team coming up very shortly.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
Music in the programme is sponsored by Epidemic Sound, perfect music for audio and video productions.
Here on The Naked Scientists, putting your questions under the microscope this week. And with me to do that are nature filmmaker Tom Mastill, psychologist Leo Smigrod, astronomer Matt Bothwell, and mathematician Ems Lord. Now, it is time to test the mettle of our teams, because we do this in the middle of these Q&A shows where we go off-piste and test the general scientific knowledge of our participants. And you're competing, you lot, for a prize beyond prize, which is the Naked Scientists Big Brain of the Month award. Team 1 are going to be Matt and Leo. Team 2 are Ems and Tom. And our two teams, we actively encourage you to confer. Now, Matt and Leo, first question. Number 1, who won the inaugural Nobel Prize for Physics in 1903 for discovering X-rays? Was it Walter Muller, John Seely Townsend, or Wilhelm Röntgen?
I think it was Röntgen. I think he X-rayed his wife's hand. There's this really famous picture where you can see her wedding ring really standing out. So unless I'm thinking of the wrong one, I think it was Röntgen.
Okay, I think that the fact that you're a physicist means that we should definitely go with that, and I like the story, so that sounds believable to me.
You're going with Röntgen, and it is a bing bong for that. You're absolutely right. I had an interesting run-in with X-rays, in fact, because about 15 years ago, we won an award in the late noughties, in those days when the Naked Scientists won awards, and they flew us to LA to go and get this award. And while I was there, I'd read this paper in one of the big science journals the week before. This chap at the University of California, Los Angeles, had said he could make X-rays with sticky tape. And while Wilhelm Röntgen did it by exciting electrons in wires, what Carlos Camara was doing was unwinding reels of sticky tape in his laboratory in a vacuum at very high speed in order to produce X-rays. And he just discovered this by accident. And we walked into the lab, and he's got piles of Scotch tape boxes up to the ceiling. And he'd got this metal sort of vat, which he'd created this device to have a sticky tape reel on one spindle, another one on another, so he could wind sellotape on and off of the spindles very, very quickly in a vacuum. And they could produce this intense beam of X-rays out the top of this thing. And they were doing it so well, they could do exactly what Röntgen did and take X-rays of their hands. And I then looked up and I said, well, you're on the ground floor. Who's in the lab up there? And he sort of looked at me and smirked a bit and said, I don't know, but I doubt they're I doubt they're fertile anymore. All these X-rays going through the floor. 1 mark to Matt and Leo so far. Well done to you. Question 2. This one is to Team 2, Ems and Tom. Which of the following types of electromagnetic radiation has a shorter wavelength? This round is called X marks the spot, so we're talking about X's. Which of the following types of electromagnetic radiation has a shorter wavelength than X-rays? What do you two think? Gamma is A, ultraviolet is B, or microwaves C?
Oh, well, this is definitely not my area of expertise, apart from probably the length of the wave, but...
I mean,
over
I haven't
to
even
you,
got
Tom.
any. The only wavelengths that I know are ones in the sea. So I think.
Okay, I mean, we can do it this mature way, scissors, paper, stone.
Wait. So what? Like, gamma is going to be micro, like stone.
Gamma rays?
Yeah.
No, wait, no. Oh, sorry, I haven't chosen.
Gamma rays, ultraviolet, or microwaves, A, B, or C. Which do you think it is?
Should we go for the first one?
I'm with you,
I think-
Ems.
Okay, we'll do this very scientifically and just go for the first one.
The scientific
Yeah.
guess. It's a scientific guess, and it is
Yes.
not that you're competitive or anything.
No,
Tom.
I was
You're
just
very
relief.
pleased. Enormous.
We're just trying to keep up here.
Yeah.
Good. So we're level pegging as we go into round 2, which is called Elementary, my dear Watson. And that's because this round is all about the periodic table of elements. So Matt and Leo, your question. There are 2 letters that don't appear as symbols on the periodic table. Q is one of them. What is the other letter? It's not Q. There's one other. Is it J, W, or Y? What do the pair of you think? Which letter is not represented? J, W, or Y, other than Q?
It's not Y.
Wow.
I think yttrium starts with a Y, right? I can't
I
think
think
of it.
that's
I can't
right.
think of a J. Can you?
I cannot think of a J. What was the other? What was the third one?
J, W, or Y?
I feel like some of those ones down the bottom of the periodic table, one of them has to have a W in it. I don't know.
So you're going for
I don't know. My vote's J. What do you reckon?
Leo, J?
Okay, let's go with J.
It's a good go with, because you're absolutely right. +1 for you. Yes, it is J. J and Q are not used as the letters in periodic table elements. Y, yttrium, you were quite right there. Actually, W does exist. It's not one of the rubbish bin category actinides, lanthanides down the bottom. It's wolfram, which is what was originally tungsten. And tungsten got
interesting.
rebranded by IUPAC, the organisation that give the chemical elements their name, about 7 decades ago. The Americans lobbied to change the name to tungsten, which is actually Swedish for heavy stone, because the Swedes who discovered tungsten and called it wolfram got it out of a heavy stone, tungsten, and so they called it tungsten. And then it got called wolfram afterwards, then back to tungsten again. So you're quite right, it was indeed J. That's not the other one that's in there. Right, +1 to you two. Ems and Tom, Team 2. A synthetic element is one of the 24 known chemical elements that don't occur naturally on Earth, or they're only present in minuscule amounts. So, what was the first such artificial element that was created? A, uranium, B, americium, or C, plutonium?
Is uranium actually naturally occurring some places?
You mean uranium? I'm thinking back Second World War. And
Yeah,
what
would
was
you have
happening
thrown
there.
any? Would you have thrown any actual real non-synthetic ones in there? Would that be a sneaky thing that is feasible?
I'm pulling my poker face.
Because I think
Cruel.
what
Is it A, uranium, B, americium, or C, plutonium?
I mean, I've never even
which is the
heard of
first
americium,
artificial element
Same here.
created.
but it makes it sound like it's going to come later, and 2 of them are radioactive. So maybe one of them, the answer is one of the radioactive ones.
Okay, I kind of
Gonna
like
have to
the
rush you.
reasoning.
This is a psychology of question setting
Okay, I
rather
say-
than any chemical
The
knowledge.
first thing you talked about was the plutonium. Should we go for that?
And I don't want to because I think I'm going to be wrong, but sure. Okay.
Okay,
Plutonium?
there you go.
Oh, there's a high five going on.
My
Yes, it
chemistry
was
teacher
plutonium.
is turning in his grave right now.
Most well known for its use in atomic bombs and nuclear reactors, uranium is naturally occurring. And in fact, it was used as early as 79 AD by the Romans, who were using uranium to colour glasses.
That's not
They
the
made
best thing
beautiful
to
glasses with that. Americium, you said, I don't even know what that is. Americium is artificial. It's in smoke detectors. You'll find it as an alpha source, which is in pretty much every home in developed countries now, where it's used to detect the particles of smoke, which get in the way of the alpha particles it's giving off.
Sneaky question, but I think we've just learnt a lot there.
Yes.
Excellent. Well, you're doing well because it's level pegging. So we're on to round 3. And Matt and Leo, back to you. This one's a tough one, excuse the pun. A rhino's skin makes up a quarter of its body weight. Is that true or false?
Wow,
can imagine
Matt,
it-
do you have an intuition?
I can imagine it being true because I know human skin makes up a surprisingly large fraction of our body weight, right?
and
you know, rhino skin is more substantial than human skin, so it doesn't seem crazy on the surface. I can imagine it being true.
Do they also have tusks that would be really heavy, though?
That's true. Yeah.
No.
Well, I mean, they do.
they?
I don't know. Well, they have horns, right? But I don't know if they a quarter.
Yeah. I mean, I think it sounds plausible.
I'm happy to say yes because I want it to be true.
So you're going
Okay, let's
true.
go with
you're going,
that.
You're going true.
Yes.
Because I actually get to use a different button now.
Oh,
You got a boob. You got boobed, I'm afraid. No. Do you think it's bigger or smaller, the number?
oh, is it bigger?
Well, it is, yeah. We are told by Will Tingle, who is our producer's lecturer. I said, have we fact-checked this? Because I was sceptical. Apparently, 43% of the weight of a rhino is its skin.
Oh, wow.
Do you know what the equivalent is for a human? Tom, you're the animal person. So what is the equivalent for a human? Your proportion of your body weight that is skin, do you say?
Well,
No
depends
bonus
how
points
you
for
measure,
this.
how deep down you go, but maybe like 4%, 5%.
Apparently it's 12.4% for the
massive.
average mammal. Yeah.
Wow.
Maybe in Wales, because of all the blubber, it's going to be a bit more. But
Yeah.
in the average mammal, 12.4%. You didn't get it on that one. So it depends. All to play for. You could take this, Matt. Ems and Tom, if you're able to pull this one off. Here we go. So this question, also in numerically speaking, round 3. What is greater, the number of nerve cells in the brain or the number of stars in the Milky Way galaxy?
Ooh. Now, if we can only recruit another team member temporarily, we'd be well in here.
Yeah, have you got a good feeling about this, Leo? Have you? I mean, a fact that I always find a bit frustrating is like, you know, that people say that the human brain is the most complicated thing in the universe, which I always find frustrating because sperm whale brains are much bigger. And I mean, I'd be tempted to go with brain. Do you reckon? There's a lot of them packed in there.
There's certainly a lot packed in there because you see all the problems that happens when these things start failing us as we age, don't you?
Yeah, not my brain. Can we have like the brain of an 18-year-old university student?
Yep.
Yeah,
Yeah.
a fresher.
A fresher.
Okay, so what are you going to go for? Are you going brains or stars? It's got the bigger number of things
Let's
in
go
them.
brains.
Yeah.
You're going to go brains?
Yes.
No!
No!
No, it's actually stars. We estimate, and Matt will hopefully corroborate my figure, that there is somewhere between 100 and 400 billion stars in the Milky Way. We're not entirely sure, but we have a closer idea about the brain because we can actually look at that more easily. It's a more practical problem. There's about 86 billion neurons.
So you're saying we don't totally
adult
know, though?
human brain.
I mean,
It's an estimate. They're using their number sense.
I'd say
it's a guesstimate. So
the answer is
that's-
still out there.
Well,
You need another
and
noise.
Still out
To
there
be
is the opportunity
confirmed.
to play for on this tiebreaker, which everyone's involved in. Now, don't confer because you'll give the game away to the other team. I will, at the end of a 30-second thinking period, after giving you 3 clues, come to each of you in turn, and the first person to get it right is going to clinch it for their team. So here we go. In which year did the following scientific breakthrough occur? Edmund Hillary and Tenzing Norgay summit Everest for the first time. Any takers so far? Anyone? Don't say the answer, just say if you think you know the answer. Leo, have you got an idea?
Nope.
Matt thinks he might have the idea.
If we get it wrong, do we get another go?
You don't get another go, but
For
do
your
you
team.
guys reckon you know? Or do you want a second clue?
think we
You're
know.
gonna take a chance? You guys? Okay, Tom, what do you reckon? Oh no!
We got a
go on
year,
then,
yeah?
Ems.
We think it's 53.
And you are absolutely right. It is 1953.
Bravo.
I remember the magazine cover.
It's coronation year
So
as
the
well.
big brain of the
Amazing.
week and month award this month goes to Tom and Ems. Very well done. We'll give you a round of applause. They were very impressive.
Thank you very much.
Right, let's get back to the questions. And indeed, still to come, we've got this question about vaporising space junk and also how whales communicate. But let's see how we go with what's in the bag so far. Ems, this question's come in. We were talking about innate abilities earlier. So this person says, are mathematicians born rather than being made? What do you think?
I think it comes down to nurture, environment and opportunity. I worked for a while as a gift and talented consultant, and we were looking at how to encourage different types of skills. And one example was trombone playing. Now, you could be lucky and grow up in a family where there's a trombone and get curious, or you could be in a school where the music teacher takes them in and everyone gets a go. How do you know you're good at something if you haven't actually had the opportunity?
Well put. Thank you very much, Ems. And I agree. I think, that it is about finding the person who's got the keen will and drive to want to do something and giving them the push and the chance to see how they get on, isn't it?
Yeah, it's multifaceted, and it's making sure we provide those environments. That's our responsibility to do that for the next generation.
Matt, this one's for you, I think. Colin says, over here in Australia, I recently saw a news report about a new whiz-bang radio astronomy array that's in the desert. The astronomers were surprised and quite possibly also annoyed that they could detect and track space junk and satellites with exceptional accuracy with this apparatus. So my question is, could we possibly use this to target and destroy the junk with a powerful ground-based laser and zap it and destroy it and vaporise it?
So the answer is hopefully. Space junk is a problem and it's only going to get worse. There's this sort of positive feedback effect you have with space junk, where if 2 bits of space junk crash together, they fragment, and then suddenly you have 100 bits of space junk that you didn't have before. And so if you cross a critical threshold, you can end up with so much space junk getting into orbit. It could be really, really difficult. So part of the solution is going to be tracking it with these radio telescopes. I think you're talking about the Square Kilometre Array in Australia. But there are different plans to get rid of the space junk, and powerful space lasers are one of the top possible solutions. For the longest time, people were thinking about using very powerful space lasers to just vaporize the space junk. A slightly more popular option these days is to use a slightly less powerful laser to just heat the space junk until it changes its orbit, then burns up in the atmosphere. That's got the wonderful name. It's called a laser broom. I think the idea is use the laser to kind of sweep the orbit clear by making everything burn in the atmosphere.
That phenomenon of giving things a push with light also has a fantastic name, doesn't it? It's the Yorp effect.
That's exactly right. And this has even been suggested as a way of re-orbiting potentially hazardous meteorites. So thinking further away than in orbit, if we can identify a meteorite that might impact the Earth in a century's time, rather than pushing it away with a rocket, if we just cover one side of it with reflective paint or something, the pressure of sunlight over the course of a century can deflect the orbit to the point where it won't be hazardous anymore.
Well, let's hope so. Tom, back down to earth and one for you. Irene is wondering, what's the most sophisticated communication in any animal species other than in humans?
Well, it's a brilliant question and one that people are looking into at the moment. A big problem is that we haven't really been looking at animal communication or non-human communication for very long, and we've got a lot of difficulties in even discerning it. We can't hear all the sounds, we can't see all of the things that are happening, we can't be everywhere, and there are communications taking place in the soil, there are communications taking place in the sea. But saying that, of the communications that we have seen, and I know I'm biased, but the communications of some cetacean species seem to be highly complex and complex in ways that are quite similar to the ways that we think of our language as being. This isn't to say that they have language, but whales and dolphins live a really long time, some species up to 200 years. Many species live in highly complicated social groups they need to hold together by communicating. And because they live in the sea, the best method of communicating is with sound. And over the last few decades, we've been starting to record a lot of these sounds. And we found that there are lots of different kinds of sounds, that the sounds are used really differently in different situations. Some of the simpler sounds we think might be things like, in some species of dolphin, for instance, signature whistles, which is analogous to a name, like a baby bottlenose dolphin would slowly learn its own signature whistle, and then that would only be used by it and the other dolphins that know it when it's around. And they've even done experiments where they've noticed that dolphins separated from their social group and then reunited, the other dolphins remember their signature whistle, their name. But it's really hard to understand the complexity of another animal's communication systems as a human being, because our whole understanding and way of describing communication is based on our own. And that's where, at the moment, there's some really exciting studies going on using artificial intelligence, machine learning, as a way in, because we've run analyses on human language using the software behind Google Translate, for instance. Google Translate doesn't know how to translate between one human language and another. It's just given enormous data sets of written or spoken human speech. And then it makes a huge array of all the relationships between the words and how they're used in these massive data sets that no human could ever spend the time to listen through or read through. And then it finds invisible patterns in human language, and it uses them to translate between one human language and another. And that's what's really exciting lots of zoologists at the moment, because these tools give us a way into other animals' communications. And the first animals that the zoologists are choosing to go after are sperm whales, and there's a huge project in Dominica to try and decode their communications.
So Tom, author of How to Speak Whale, pins his colours to the mast and says, in his view, the answer, Irene, is whales. Leo, over to you. It makes logical sense, obviously, the way our brains operate. That will influence what we believe in. And therefore, can we flip it round? And can we say that what we believe in will, in turn, impact the way that our brains are shaped and work? Is there a two-way street of learning, effectively? What you do shapes your brain, and the way your brain is shaped shapes what you do?
That's a great question, because in essence, sometimes we forget that our beliefs are part of our brains. They reside in our brains. Our beliefs are an extension of us, because where else would they be? And so when we're thinking about this in the context of how information can affect our brains and our brains affect the kind of information we're receptive to, we can definitely see those bidirectional links whereby some individuals, for instance, are highly attracted to certain kinds of information and their brains will soak it up. And at the same time, the kind of information that we're exposed to, whether it's extreme information or scary kind of settings or the environments that we're positioned in, that can sculpt our brains too in the way that any other kind of experience can. The same way that stressful experiences or adversity will change our brains, so will the kinds of information that we're embedded with, the kind of information that we inhabit and internalize deeply.
There are limits on how plastic or mouldable our brains are, aren't there? And there's this question of, as you get older, whether you lose some of that. And this is probably relevant to EMS and mathematicians, isn't it? They do their best work when they're young, apparently. She's nodding, so probably is. Is that true?
I mean, we see that young people do have the greatest brain plasticity, and that does get reduced over time. We can always improve, kind of train, make sure that, because we talked about how experiences shape our brains, the more that we engage in flexible and creative acts that kind of stretch our brains in all sorts of directions, the more that we can sustain that kind of plasticity and flexibility over time.
This is The Naked Scientists with me, Chris Smith. And this week we're answering your science, technology and medicine questions. With me to do that are nature filmmaker Tom Mustill, psychologist Leo Zmigrod, astronomer Matt Bothwell and mathematician Ems Lord. And if there's something that you've been pondering on and you'd like to get it into a programme like this, our door's always open. You can email chris@thenakedscientist.com or you can tweet us. It's @nakedscientists. Still to come, the key to keeping our oceans clean. That's what we're going to hear about. Matt, one for you from Peter, who says, we've heard that the US is locked in a space race with China and the country needs to watch out that its rival doesn't dominate lunar resources, or so says NASA's top official. So why is space science so often a point of competition, he says, rather than collaboration?
I think this is a question that I would also love to know the answer to. I think the answer is that the people that are deciding that it's a competition are the politicians. It's not the people actually doing the science. NASA is famously beholden to this thing in US legislation called the Wolf Amendment, which means that they can't put any money into any sort of collaboration with China. I think the politicians' sort of justification for this is that space travel and space launches, in terms of tech, isn't a million miles away from missile launches. And so if you give people insight into your space capabilities, you might be giving them a bit of insight into your military capabilities. I think most scientists just want to get on with it, to be honest. I think Martin Rees, the Astronomer Royal here in Cambridge, said that America going along with this Wolf Amendment and refusing to cooperate with China was a huge own goal. And I think most scientists would agree. I think scientists tend to want to collaborate, right? Even at the height of the Cold War, you had mathematicians, sneaking across the border to exchange their number theory notes and stuff like that, right? So I think scientists want to collaborate, even if sometimes politicians don't let us.
But it's also it's a sort of friendly competition against frenemies up to a point, isn't it? It's quite good sometimes to have competition and regard yourself as in a race, because it tends to make people dig deeper and go that extra mile. Things tend to get done faster if people think they're racing for something, not just doing something.
Yeah, that's exactly true. I mean, so the first space race between the USSR and America wouldn't have happened, right, if they weren't in competition. There's a famous quote, I forgot who said it, that war is the continuation of politics by other means, right? I mean, maybe the space race is a continuation of war by other means.
We could perhaps get one of our listeners to tell us who said that. Thank you very much, Matt. Nigel, who's a teacher, he says he's looking for some tips on how he can get Pythagoras' theorem and bring it to life a bit for his students, and says, any tips? Can you help?
Oh, wow. Pythagoras happens to be one of the subjects that I studied at uni. I got fascinated by all the different ways that you can actually prove Pythagoras' theorem. There's a lot, if you've got nothing to do later.
I mean, just for those not in the know, this is you have a triangle that's got a right angle in one side.
Exactly.
And if you add the square of one side plus the second side, then they add up together to the square of the long side.
Okay,
that's
so,
what he's saying, isn't it?
Yeah, I mean, that's great because we've got that procedural fluency, we know the rule. But the thing is, do we actually understand what it means? And I think there's a huge difference there between being able to recite it and understand it. Now, there was this great geometry teacher, and what he did is he drew the triangle on the board, the right-angled triangle, and then on each side of it, he drew a square. So imagine you've got a right-angled triangle and you've got 3 squares of different sizes. Now, imagine you've got those squares and you've made them out of gold, okay? You've beaten gold. Now, if you want to engage your students, why not offer them which one do you want? Do you want that single square or do you want the 2 smaller squares? Now, if you've really understood, if the class has really understood what Pythagoras is about, they're going to know it's no contest because of the sum of the squares.
They must be the same.
Okay? What happens when you do that with a class? They tend to go for the larger square. Now, part of that might just be, I want the biggest, it's mine, put my arms around it. But it's also saying something about the understanding and not picking up on the, I wonder what's going on here. So I think choosing activities like that, where it goes deeper onto the understanding, the conceptual understanding, rather than just focusing on the fluency. Yes, we need to know the facts, but there's no point in knowing them if you can't apply them. I mean, you get builders nowadays, they'll talk about having a 3-4-5, to get your roofs correct at the angles. And they may not associate that with Pythagoras, which is a shame because, here we have a system at the moment where people are saying they don't understand why they do maths at school, and somebody's going, I want to go off and be a builder, why do I need Pythagoras? And then they'll go and use a 3-4-5 to try and get the roof right.
You're so right, though, because I can remember I must have been about 8-9 years old, and my maths teacher was trying to introduce the concept of area. And when you're that age, when someone has centimetres or metres squared, it just doesn't really mean anything to you until she said, I'll tell you the story of a monk who used to walk around the courtyard at the monastery and all 4 sides of the cloister. And the cloister was paved in 1 metre wide flagstones. And he found out that he could work out exactly how many there were and the area of them if he walked and counted them, or he could do it the quick way and times that side by the number along that side. And that vivid picture that it created in a 7-8-year-old brain meant I engaged with it. And rather than it being foreign language, metre squared, centimetre squared, what on earth does that mean? Now I actually can understand what this is about.
And you've got a visual there, and visuals are so important in mathematics. You go throughout mathematical history, and when we've got the visual, we've often made the breakthrough. I mean, a really famous example is Florence Nightingale. I mean, there she was in the Crimea, lots of soldiers injured, but many more were dying of their wounds. And she was trying to campaign for better conditions for them. And so she collected the data, had all the lists, and you think, as a mathematician, you got it sussed. You've got the data, you present it, and you win the argument. But they were just lists of numbers. And until you bring it alive and do a visual, which is what she did with an area map, you suddenly realise the huge number of casualties. So it's another example. If you do a visual, either someone walking around a courtyard, beaten gold, do you want the gold on the larger triangle, on the square? Or is it the area of the soldiers and the ones who died from wounds?
Let's turn to Laura's question, who says, how does overfishing or bycatch, when people catch stuff and they didn't want to catch it, so they often end up killing it and it's lost. How does that rank amongst or against other threats to marine life, things like plastic pollution and climate change?
I mean, this is a very hard question to answer because those three problems, which are just some of the problems that like living creatures face in the oceans, they really depend on what kind of animal you are, where you live, and what kind of timescale you measure it over. So you can overfish a reef and then stop fishing, and then that reef can be recolonized often. And within a few generations, you can have a vibrant community. But it can be absolutely devastated if you really overfish all the places around nearby, or if you fish things to extinction and they can't bounce back from that. Plastic pollution, I've seen the impact of whales getting tangled and dying because they're caught in ghost nets and other plastic pollution. We can measure that very well. But what we can't measure and we don't really understand yet is what happens to all the microplastics that are so ubiquitous now. We know that I think some of them, is it recently we found they could cross the blood-brain barrier? You know, these are going to be generational effects, and they could be things that we can't measure or can't fix until they're too late. And with climate change, there are already winners and losers in the oceans emerging. In whales, obviously. For instance, in Antarctica, among the whale populations, as the ice melts, that's making some places available to whales that couldn't really navigate around ice or weren't really comfortable. So their populations are going up. But other whales are losing the krill that they fed off, or they're less comfortable in those warmer waters and they're having to move. So that's a really bad answer to the question, because I don't know, but all of these things are so interlinked and they depend on where you are and the scale of the problem where you are.
Yeah, I mean, it's not a simple answer, is it? It's not just one thing, and that's the complexity of life on Earth. It is a web, and it's a complicated one at that. Leo, one about hallucinations for you. This person says, what is a hallucination? What makes them happen? What's going on in the brain?
So hallucinations are basically sensory experiences that are not rooted in any external stimulus. So there's no outside event actually happening, but the person is experiencing maybe an auditory hallucination where they're experiencing voices, they're hearing voices in their head. And similarly, there's visual hallucinations or tactile hallucinations. And it's interesting to think about why the brain hallucinates and what the brain looks like when it hallucinates. And actually, in some of the research that my colleagues and I have done, we've looked at what a hallucinating brain looks like in the brain scanner. And we wanted to know whether a visual hallucination that you see looks kind of the same to the brain as an auditory hallucination. And we kind of had this hypothesis, this theory, that there would be one area in the brain that would be able to distinguish between real and unreal information. So basically that it would be able to distinguish between a hallucination and a real sensory perception. What we did find is that the hallucinating brain looks exactly like the perceiving brain. And that's fascinating, that the brain doesn't seem to actually distinguish for itself between a hallucination and a real event.
Goodness. So when people say that it really seemed real to them and they're unshakable in their belief, if you try and dissuade someone who's having a hallucination that it's not real, that's why they so strongly disbelieve you, because to them it really is. It's exactly the same brain wiring firing off as when they're having that experience for real, which is why it feels real to them.
Exactly.
Tom, let's just return at the end of the programme to really the point we began at. You film wildlife documentaries. And, I mean, you told us about this staggering experience you had out while watching. But what's it like actually on the ground when we are the beneficiaries of these lovely programmes with this amazing footage? And I think people have begun to demonstrate how they get some of that footage in some of the films. It's become en vogue, hasn't it, to show what it took to do it. How hard is it to go and get that footage? Is it literally hours and hours of tape that most of it ends up in the bin for 5 seconds of sequence to show people this one-off event?
Well, you don't record all the time. There's actually a really neat function on many film or video cameras where when something happens and you press record, it will also save the previous 5 or 10 seconds or 300 frames or 1,000 frames if you're rolling high speed. So you don't need to record all the time if you've got that. In the making ofs, the behind the scenes, often you see people sort of waiting, and people often say like, well, you've got to be very patient. I mean, my experience has always been that if you're in the lucky position that you're just waiting, that's great. Because most of the time, like, one of you's got a maggot hatching from your skin, or you've run out, you forgot to charge the batteries, or the animals migrated somewhere else, or, you know, like, your visas haven't come through, or you've dropped the camera in a lake. So if you've actually managed to be in the right place at the right time, and all you've got to do is wait, and plus, there is a certain self-selection, like the kind of person who becomes a wildlife camera person is probably quite happy by themselves waiting. But I mean, there's a lot of uncomfortable. I mean, I made a documentary called The Batman of Mexico, where we went and filmed bats, and that was really the main challenge. There was that humans are awake in the day and bats are awake at night, so we just got really tired. And then if you have to spend time in bat caves, you're basically sitting underneath them while they're defecating and urinating continuously, and the caves are often full of cockroaches, and sometimes you have to. We were just wearing like flip-flops and shorts and vests because it was incredibly hot, but we were wading through like knee-high guano, and there was like centipedes on top of it, and sometimes we filmed the snakes that were catching bats, and we had to like lie in a pitch darkness, and the only person who could see was the camera operator, and he could see because we didn't want to disturb the bats. So we had to film with a wavelength of light they couldn't see, but we couldn't see that either. So he could just see all these snakes coming out of the walls and dangling around our heads. And so all we could hear was him groaning in terror, and we could just imagine it. So there is also, but that's all kind of fun, if you like that kind of thing. But I mean, each animal has its own challenges. And I think the people who are drawn to film those animals often kind of like those challenges.
So Ems was talking earlier about the importance of ambassadorship in her subject, which is maths. I think you've just done wonders for just drawing people into being a wildlife photographer.
Well, it's a highly competitive field, and if I've put anyone off, I'm delighted because it will just extend my career. No, it's really nice. Join in.
And there we absolutely must leave it. Tom Mustill, thank you very much indeed. Also with us this week, Ems Lord, Matt Bothwell and Lior Zmigrod. Next time, Dry January is the subject to Whet Your Appetite. We'll look at the history of alcohol and brewing, what constitutes a safe level of drinking, if there is one, and we'll discuss the alcohol substitute that makes people a bit merry, but for less long and without the liver damage or the hangover, allegedly. The Naked Scientist comes to you from the University of Cambridge's Institute of Continuing Education. It's supported by Rolls-Royce. I'm Chris Smith, and until next time, goodbye.